Oh, okay. Oh, we're good. Okay, prove f of x equals 2x squared is uniformly continuous on the interval from 0 to 1. Okay, so we want to recall that if f is a function is uniformly continuous if for all epsilon greater than 0 there exists a delta greater than 0 such that for, well, we're using x and z, for all x and z are elements within the interval 0 to 1, open interval 0 to 1, with our absolute value of f of x minus z of x, f of z, f of x minus f of z is less than epsilon whenever x minus z is less than delta. So therefore, because we're working with x squared, right? We're going to put fx, that'll be f of x is x squared, and f of z is going to be z squared, and that's less than epsilon. Okay, so we want to prove that f of x equals x squared is uniformly continuous on the interval 0, 1. Uniformly continuous on the interval from 0 to 1. So in our proof, we're saying let epsilon be positive, right, or greater than 0. But we have to choose a delta. Well, we don't know what that delta is. So we're going to figure that out on the scratch paper and then go back and write our proof. Then from that, then for all x and z that are elements in our interval from 0 to 1. Okay, so we have a problem. We're going to write this proof, but we got a problem. We need to find what delta is. So we're going to call this our scratch work. So we're going to figure out our scratch work first. And my green is running out. So I'll use blue instead. So we're going to figure out our scratch work and then go back and write our proof. So here we have f of x, the absolute value of f of x minus f of c is less than epsilon. Whenever x minus c is less than delta. Okay. So since x and z are elements of our interval inside of 0, 1, then x has to be less than 1 and z has to be less than 1. So we're going to remember that when we work through our problem. Okay, so we take this f of x minus z of x, and so that's going to be f of x, we know that's x squared. Z of x will be z squared. So that'll be x squared minus z squared, and that's less than, inside absolute value, and that's less than epsilon. Okay, so if we factor that, that's x minus z times x plus z. All right, so since okay, from here we can split that, right? We can say, all right, well, this is x minus z, absolute value of x minus z, times absolute value of x plus z, and since x is less than 1 and z is less than 1, then x plus z must be less than 1 plus 1. So we can say here that this is less than absolute value of x minus z and 1 plus 1. Because x is less than 1 and z is less than 1, then they both must be less than this, must be less than this. So that's going to give us, from there, that's going to give us, that's less than x minus z. So 1 plus 1 is 2. Okay, well, we know that x up here, we know that x minus z is less than delta. So we can say here that x minus z is the same as delta. So that would be delta times 2, and that would be less than 2 delta. And since f of x minus f of z is less than epsilon, that absolute value is less than epsilon, then we can say that x squared minus x squared minus z squared is also less than epsilon. And so that means that we can take, that means that this 2 delta, if we took that less than 2 delta, would be less than epsilon, because this is equivalent to this here is equivalent to x squared minus z squared, because that's what we got here. So we went from x squared minus z squared, we factored it, and we said that x plus z had to be x is less than 1, z is less than 1, so that would be less than 1 plus 1. And x minus z is the same as delta, so we get 2 delta. So therefore, that 2 delta is going to be also less than epsilon, because x squared minus z squared is equivalent to 2 delta, so 2 delta is less than epsilon. So if we divided both sides by 2, we get delta. We can say, all right, delta is equivalent to epsilon over 2. So now we can go back and start our proof and put that into here. Delta equals to epsilon over 2. So going back to where we started from, so now we can write up our formal proof. And we want to prove that f of x equals to x squared is uniformly continuous on our interval from 0 to 1. So now we can say let epsilon greater than 0 choose delta is equal to epsilon over 2. Let epsilon be greater than 0. We choose delta equal to epsilon over 2 such that, so now we're just basically rewriting what we did here, all such that all x and z are elements of our interval from 0 to 1 with f of x minus f of z is less than epsilon whenever x minus z is less than delta. Okay, so now we're taking what we did in our scratch work and we're working backwards. Okay, so from here, we have x squared minus z squared equals to epsilon. We have, so we're taking f of x and we're placing x squared in there. X squared minus z squared is less than epsilon. Okay, so from here, now we're just putting in, now we're basically just repeating what we did on our scratch work. So now this will factor x minus z times x plus z, and that's equivalent to x minus z times x plus z, and since x and z are elements of a interval from 0 to 1, then x is less than 1 and z is less than 1. So therefore, we can substitute in x plus z is less than 2. The absolute value of x plus z is less than 2. And since x minus z is less than delta, then we can substitute 2 in for x plus z, and we can substitute delta in for x minus z, and all of that is less than epsilon. So 2 delta is less than epsilon. And so from there, since we chose delta is equal to epsilon over 2, then we can say that 2 times epsilon over 2 is equivalent to epsilon, because the 2's cancel out, and we've proven it. And proof complete.